30 key takeaways from chapters 1 through 2 of Until the End of Time, which lay the foundations of our understanding of time, space, and entropy, each paired with a real-life example or story. 1. The universe is governed by unchanging physical laws. Takeaway. All phenomena, from the cosmic to the everyday, obey universal laws. Example. Newton's laws explain both the orbit of planets and a ball rolling down a hill. 2. Time emerges from change. Takeaway. Time is not a mysterious flow, but a way to quantify change and process sequence. Example. When you watch a plant grow, each change marks the passage of time. 3. Entropy measures disorder. Takeaway. Entropy quantifies how spread out energy is and why systems evolve toward disorder. Example. A neat room eventually becomes messy without effort, mirroring increasing entropy. 4. The arrow of time is set by increasing entropy. Takeaway. Time's one-way direction comes from the natural tendency for disorder to increase. Example. Once an egg is scrambled, high disorder, it cannot unscramble back to its ordered form. 5. The early universe had exceptionally low entropy. Takeaway. The Big Bang produced an extraordinarily ordered, low-entropy state that allowed structure to emerge. Example. Just as a perfectly arranged set of dominoes is rare, the early universe's order was a unique starting point. 6. The Big Bang gave birth to time and space simultaneously. Takeaway. The origin event created not just matter, but also the fabric, space-time, in which events occur. Example. Imagine a fireworks explosion that not only disperses light, but also sets the stage for the unfolding show. 7. Space and time form a unified space-time continuum. Takeaway. Rather than being separate, space and time are interwoven, a concept essential to relativity. Example. GPS systems must correct for time dilation effects due to Earth's gravitational field. 8. Entropy drives the evolution of structure. Takeaway. While overall disorder increases, local pockets of order, like stars or living cells, can form by expelling entropy to their environment. Example. A refrigerator keeps food organized, low entropy inside, by dumping heat in disorder outside. 9. Local order is achieved at the cost of global disorder. Takeaway. Systems, including living organisms, maintain order by exporting entropy. Example. Your body stays organized by releasing heat and waste, increasing the disorder around you. 10. Time's perception is linked to entropy's flow. Takeaway. Our sense of past, present, and future is deeply tied to irreversible changes caused by entropy. Example. Mixing cream into coffee creates a one-way process. You experience time as a sequence that cannot be reversed. 11. Physical processes are statistical, not deterministic on the microscopic scale. Takeaway. Entropy arises from the overwhelming likelihood of many disordered microstates versus one ordered state. Example. Shuffling a deck of cards will almost never return it to perfect order by chance alone. 12. The universe's expansion continues to increase entropy. Takeaway. As the cosmos expands, energy becomes more dispersed, driving up overall entropy. Example. Over billions of years, galaxies drift apart, making the universe increasingly spread out. 13. The early uniformity of the universe was crucial for structure formation. Takeaway. A nearly uniform beginning enabled small fluctuations to eventually seed galaxies and stars. Example. Tiny ripples on a calm pond can grow into waves when disturbed. 14. Time and entropy are inextricably linked. Takeaway. The irreversible increase in entropy gives time its direction from past to future. Example. Once ice melts into water, it marks a forward march of time that can't be reversed naturally. 15. Low entropy conditions are rare yet vital. Takeaway. Exceptional order, low entropy, in the early universe was a rare condition that made complexity possible. Example. Just as a perfectly organized library is rare without constant upkeep, The universe's initial order was extraordinary. 16. Energy dispersal is inevitable without external work. Takeaway. In isolated systems, energy will naturally spread out, increasing entropy. Example. A hot cup of coffee cools down because its heat disperses into the cooler room. 17. The second law of thermodynamics governs all natural processes. Takeaway. In any closed system, processes occur in the direction of increasing entropy. Example. Wood burning in a fireplace transforms into ash and smoke, an irreversible change. 18. Irreversible processes give time, it's one-way flow. Takeaway. Because many natural processes cannot be undone, we experience time as moving forward. Example. Once you walk away from a campfire, you cannot unburn the wood. 19. Local decreases in entropy are possible through energy input. Takeaway. Order can be maintained or created if energy is supplied from outside the system. Example. Air conditioners use energy to cool and declutter a space, lowering local entropy while increasing it elsewhere. 20. Entropy explains why some events are statistically irreversible. Takeaway. The improbability of reversing high entropy events underlies the irreversible nature of many phenomena. Example. Spilling milk is virtually impossible to reverse because the milk molecules spread out too widely. 21. Complex systems arise from simple physical rules. Takeaway. The ordered structures we see, from galaxies to cells, result from the interplay between basic laws and statistical tendencies. Example. Lego blocks snapped together in countless ways can form intricate buildings if guided by a set of rules. 22nd. Entropy helps define the quality of energy. Takeaway, not all energy is equal. Its usefulness depends on how concentrated or dispersed it is. Example. Freshly charged batteries are high-quality energy sources compared to the dispersed heat in a warm room. 23. Our everyday experiences reflect cosmic principles. Takeaway. The same principles that govern the cosmos also underlie mundane phenomena. Example. Melting ice in a drink is a small-scale example of the universe's drive toward higher entropy. 24. The growth of order in nature is always temporary. Takeaway. Even the most organized systems eventually succumb to entropy over long timescales. Example. A perfectly arranged bouquet will wilt and disintegrate over time. 25. Our perception of time is rooted in physical change. Takeaway. We sense time passing because we witness changes, most of which are irreversible. Example. Watching the seasons change from spring to winter illustrates time's unidirectional progression. 26. The universe's fate is tied to entropy's inevitable increase. Takeaway. Eventually, as entropy maximizes, the universe may reach a state of heat death where no work is possible. Example. Think of a slowly cooling cup of coffee that eventually reaches room temperature and can no longer do anything useful. 27. Local miracles of order require external energy. Takeaway. Any localized decrease in entropy, order creation, is fueled by energy from an external source. Example. A city stays illuminated and organized at night by drawing on power plants that release waste heat. 28. Statistical fluctuations can occasionally lead to order. Takeaway. Rare fluctuations can momentarily create ordered states in an otherwise high-entropy system. Example. In theory, a few air molecules might spontaneously cluster to form a tiny transient pocket of order, though it's extremely unlikely. 29. The fabric of reality is interconnected by energy, matter, and information. Takeaway. The interplay between energy dispersal, entropy, and structural information underlies all phenomena. Example. The detailed design of a smartphone is a product of both high-quality energy inputs and intricate manufacturing processes that impose order. 30. Understanding entropy deepens our appreciation of life's impermanence. Takeaway. Recognizing that all ordered systems are temporary helps us value the beauty and fragility of our world. Example, just as a beautiful sandcastle is destined to be washed away by the tide, every human endeavor is transient, inspiring us to cherish each moment. Each of these points builds a picture of how time, space, and entropy form the bedrock of our physical world, a theme that Brian Greene artfully develops in the opening chapters of his book.